Welcome back, physics fans. We're moving on with part 2 of lesson 1. Let's call it lesson 2. And we were talking about momentum in one dimension. Momentum, P equals mv, or, MVP. Sorry, here we go. Let's do a lab together. And I'll do all the work. You just pay attention. See if we can get the results out of here. Here is a little collision simulator lab. Let's just watch what happens when I click on play. Boom. And one's traveling, and they hit. And we can show the values, their velocities, and their momentums. And watch what happens. Bam. And we can replay it. And we can type in the values of the masses and stuff like that. We can also check to see if they're going to collide, if they hit each other, and how much they stick to each other. So this is like total sticky here. They're going to stick in. What's going to happen here? Bam. So we're going to play around with it and take a look at what we can do. So we'll start off with 100% elastic because I know the lab. Here it is. It's on your handout. Elastic collisions. Move the elastic all the way to the 100. Here we go. So we're doing it with the elasticity of 100%, which I've set it. 3 and 2, mass is 3, 2, and the other mass is 3, and it's 0. And, well, let's see, right now, mv, and this is to the right. I'm already just saying to the right, and if it's the opposite way, it'll be negative. So let's see, can I write in here? This is going to be 6, and this is going to be 0, so the total momentum beforehand is positive 6. And let's see what happens afterwards. So mass is 3, and the speed was 2. Okay, so let's go back to that. And the speed here is 2. So let's play it through. So the speed, this guy's not 2 anymore, and this guy is 2. So it looks like it kind of exchanged, and this guy's 0. 0, okay, good. So the velocity of this guy afterward is 0. So his momentum is 0. And afterwards, this guy is 2. Boom. And so that is going to be 6. So afterwards, we add up that and that to get 6. So it looks like it stayed the same. I wonder if that's going to be the thing of this. Well, it's the next one is 3, 2, and the other one is 1 kilogram. So it's the same scenario, except reduce this guy down to 1. So smaller. Let's slow down that sim speed because that seems to have happened way too fast. And let's play it. Bam. So it went to 1 and 3. 1 and 3. So this is 6. This is 0. So the total is still 6. And afterwards, the velocity was 1 and 3. Yeah, I'm slow, but here we go. 1 and 3. And 1 times 3 is 3, and 3 times 1 is 3, so 3 and 3 is 6. Okay, let's say 1 and 2, and 3 and 0. And see what happens. Okay, and one more simulation here. Let's make them the same mass. Let's make 1 and 2 and 1 and positive 1. So going away, it's going to hit it from behind as it goes along. Bang, and see what happens. Here's a new one. Will they swap? Will they swap? Boom, they did. They swapped. Okay, let's restart it. Let's go -4. No, I guess it's got to hit. Let's go 3. This guy is -0.5. Yeah, they swapped. Cool. Okay. Next one, let's calculate this up now. This is going to be 6, and this is 6, and this is 2, and this is 6. This is 0, and this is 1. This is, oh no, this is 0, and 0, and -6. Okay, so we're going to do these ones, 3, 2, and 3, 0. So let's go over here and reset it. And change the elasticity down to low. Okay, 3, 2, 3, and what's going to happen? Sim speed down, slow it down. They stuck together, and oh, elasticity is not 0, it's 1. 0. Okay, good. So they both went off at 1. That made it 3, and this guy had 1. That's 3, and 3 and 3 is 6. Even though they stuck together, it still stayed the same. So let's go 3, 2, and 1. And let's see if we can predict what's going to happen. Total is 6, total is 2. Let's go 3, 2, 1, 3, 2, 1, 0. So this total momentum is 6, this total momentum is 0. So the total is 6. Afterwards, we want the total to be 6 as well. So what do? What do you think is going to happen? 2/3? No. 3/2. 1.5 each. 1.5 times 3 is 4.5, and 1.5 times 1 is 1.5. So this is going to be 6. It's 1, 2, and 3, 0. 1, 2, 3, 0, play. Bam. Half each. Interesting, eh? I think so. 0.5, half of 1 is a half, and this is 0.5 times that is 1.5, 1 half plus 1.5 is going to be 2. Yay. And let's go 3, 2, and 3, negative 2. 3, 2, 3, negative 2. Oh, what's going to happen? 6, negative 6, total 0. What's going to happen? Bam. They both stop. Cool. Let's just get these numbers in here. That was 0, this was 0, this is 0, 0, 0, 0. Because they stop, there's no momentum. So the momentum before is the momentum after. It doesn't matter if they're really bouncy or really sticky or anywhere in between. The momentum is constant. What can we say about that? So example 2, that's just before we come down to that momentum is a conserved quantity that we're going to come up with. You can spy down there, and we know that you have. In the collision below, seen below, which vehicle experiences the larger force? The truck, much bigger, same velocity as the car, maybe even some lower velocity, who knows? They hit. What's going to happen? Use principles of physics. Which one's going to experience the larger force? Of course, the truck is going to hit this. It's going to experience Newton's third law. They both experience the same force. For every action, there's an equal and opposite reaction. Equal. Why? Newton's third law. For every action, there's an equal and opposite reaction at the same time. Equal forces, opposite in direction. On different objects. Of course, there's two different objects because there's two blocks, different forces, right? And collinear, they're in the same line when they hit each other. It's fine. All right. So why is it that the car and driver are almost, the car and the driver in the car is almost always worse off? Right? Because you want to be in the bigger one. Well, if they have the same force, and we have the big truck, we'll get a small acceleration. But if we have a small car, we might have to get a larger acceleration. And a larger acceleration, yeah, people in the car don't like fast accelerations. G-forces, you break bones, it's nasty. You want a bigger truck, a bigger mass. For collisions in a closed system, the contact forces are governed by Newton's third law. So forces are equal and opposite, which implies that the momentum change is equal and opposite. So if the forces are equal and opposite, notice the negative sign. And of course, if this one pushes on this one with the same amount of time that this one pushes on that, it has to be because they're in contact. So we multiply it by the same time. F times t is change in momentum. F times t is the change in momentum. What does this mean to say that the momentum change is equal and opposite? For instance, if the car, in the last one, it loses 20 units of momentum, what happens to the truck? The truck will gain 20 units. Now gaining, well, that's because the sign is going to be a gain. As one goes up, the other one has to go down, but that's only the change in the sign means the direction. So if this guy is going 20 this way up here, this guy's going 20 this way, when they hit, they'll be stuck and they won't be moving. They both lose. Okay, Since momentum change is equal and opposite, the momentum for that system is not gained or lost. It is simply transferred to the other object. This means that momentum is conserved quantity. We've seen that. So is there such a condition that the car and truck end up at rest? Yes, an example here. Here's the truck that's much bigger than the car, but moving faster. The product here is 24,000. Product here is 24,000. But this one's this way, this one is this way. When we add them up, we get 0. So they'll stop. So the law of conservation of momentum can be written many different ways. The sum of momentums beforehand have to equal the sum of the momentums after. I love that, but that's really high end. The momentum of 1 plus the momentum of 2 equals the momentum of 1 after plus the momentum of 2 after. Vectors, m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. That's what I have written down here, where the prime just means after. So we're not using i's and f's because there's just so many there. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Pretty good, eh? I've been teaching it for 20 years, I think so. Well, maybe 30. A 30-gram bullet moving at 250 meters per second strikes a 5-kilogram block of wood at rest. So this block of wood is at rest and sticks in it, so it stays stuck in it. If the bullet and the block move off together after the collision on a frictionless surface, it's just going to slide. Let's write down the momentum equation. So this is 0.03 kg, and the velocity is 250 meters per second, and this is 5 kg. So we go momentum before equals momentum after, and then we write down m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. For two objects, that's what we do. If there's 3, we would add another one on each side. So this is 0.03 times 250, and positive will be to the right. If it ends up being negative, it's going left. I don't think so. Plus, and this is 5 times 0. And now they're kind of stuck together into one. It's almost like one object. This velocity and that velocity are going to be the same because it's the same object. So if that's the case, I'm just going to go m1 plus m2 in the velocity.
And that equals 7.5, that's 0.03 times 250. And the masses together on the right hand side are 5.03. So we're adding them together. 7.5 divided by 5.03. And we get 1.491 meters per second is the velocity. Excellent.